We have been studying functions from real numbers to real numbers, or from n-dimensional Euclidean space to real numbers. In this video, we will study more general maps, that is, maps from n-dimensional Euclidean space to m-dimensional Euclidean space, where n and m can be 1, 2, 3, or any natural numbers. Now, let's say S is a subset of n-dimensional Euclidean space, and let us assume there are a bunch of functions, f1, x1, x2, and so on, up to xn, that is from S to real numbers, and another function, f2, with the same set of variables, and so on, and suppose there are m such functions. Then if we combine these functions together to define, so for each element in our n-dimensional space, a1, a2, and so on, an, in S, we can define a point in m-dimensional Euclidean space that is f1 of A, f2 of A, and so on, and fm of A. That this point belongs to this space. Okay. By this mapping from here to here, from this A to this point, we can define a function that is, let's say, f of x is equal to f1 of x, f2 of x, and so on, fm of x, where x is an element of S. So this function is, this map is a map from S to m-dimensional Euclidean space. Here, this n and m can be any natural numbers. So let's see a few examples. For example, if n is equal to 1 and m is equal to 2, we might have a function from one-dimensional space to two-dimensional space. So let's say S is a closed interval between 0 and 1. So this is a subset of R, real numbers. Okay, so we can define a function by mapping each t in S to a point f of t and g of t in the two-dimensional space. So this is a mapping from one parameter, one variable to two real numbers. So that is a point in two-dimensional space. This defines a path, assuming f and g are continuous functions of t, this corresponds to a path in the two-dimensional plane. So something like this. So when t is equal to 0, it's somewhere here. When t is equal to 1, it's somewhere here. So each point on this plane corresponds to this point. So it's a path in 2D space. Another example, let's say we have n equal to 2 and m equal to 3. And consider three continuous functions, f of uv, and g of uv, and h of uv. And each of these is defined on an open region in two-dimensional space. Okay, so we can define a map from U to the three-dimensional Euclidean space by assigning each pair U and V to this point in the three-dimensional space. So if we specify these two numbers, we can specify these three numbers by using these functions f, g, and h. So this is an example of a mapping from two-dimensional open region to three-dimensional space. In these examples, we have assumed that these functions f, g, or f, g, h in this example, they are continuous functions. Okay, but we would like to define the notion of continuous map of this map or this map itself, themselves. Okay, so if we have a general map from U to R, let's say M, where U is a subset of n-dimensional space. Let's say this is a map called F. How do we define the continuity of this map? The idea is a natural extension of the continuous function in the case of m equal to 1. So in that case, the continuous mapping function was defined as this. So when limit of f of x, when x approaches a, is f of a. Of course, x and a are supposed to be points in the domain of f. Okay? And f of x and f of a are real numbers. Okay, so how can we extend this idea to general maps from n-dimensional space to m-dimensional space? That's the question. So to consider this, let's go back to the definition of this limit. Okay, so we use the epsilon delta argument. So that was for every epsilon that is positive, there exists a delta that is positive. And for all x in the domain, let's call this D domain, if x is in the delta neighbor of A, then the difference between f of x and f of a is less than epsilon. Okay, if this proposition holds, then we say the function f is continuous at a. Okay, so this was the definition. Now, in the case where the codomain is the set of real numbers. Okay, but here we want to extend this to general maps when m may be greater than 1. Okay, in that case, the only problem is this part. Okay, so this means absolute value of the difference between f of x and f of a. But in the general map, this is a vector, or it's a tuple of m real numbers. So we cannot use this absolute value, but instead we can use epsilon neighbor. So instead of this, we write f of x belongs to the epsilon neighbor of f of a. Just by this replacement, we can extend the notion of continuous map to general maps. Okay. In other words, as we have seen in a previous video, this belonging to delta neighbor or epsilon neighbor can be translated in terms of the vector norms. Okay, so x belongs to delta neighbor of A. This is the same. This means the same thing as this, x minus A. So this is the difference between x and A as vectors, and take the norm. This norm is less than delta. And similarly, so this norm is the norm in norm in Rn. Okay, and f of x belongs to epsilon neighbor of f of A is the same as, it's equivalent to f of x minus f of A less than epsilon. And this norm is same as it is defined in the m-dimensional space. Let's write it. M-dimensional space. Okay. So just by this replacement, we can extend the notion of continuous map for general maps. What this definition of continuity means is the following. Let's say we have the point A and point X. And these points are mapped to some point f of x, and let's say this point and this point f of A. Okay, so this is a subset of R of n, and this is a subset of R of m. Okay, and let's say this point, and let's say the distance between f of x and f of A is less than epsilon. Okay, so let's draw a circle around centered at f of A. So the radius of this circle is epsilon. Okay, so the distance between f of x and f of A is less than epsilon. Okay. However, if small this epsilon is, we can always take delta that is small enough such that if the distance between x and A is less than delta, so this is the circle of radius delta, or sphere of radius delta. So if x is within this sphere, then the resulting point of f is, wait a minute, is, yeah, f is within the this sphere centered at f of A with radius of epsilon. If this holds, if this can be achieved for any epsilon or any epsilon, then we say this map F is continuous. The following theorem is very convenient when we want to check whether a map is continuous or not. So suppose S is a subset of n-dimensional space, and we define a map F of x by this f1 of x and f2 of x and so on to and fm of x. So f is from S to the m-dimensional Euclidean space. Okay, let's define a map like this, and we say we have f is continuous if and only if f1, f2, f3, and so on, fm are continuous. Okay, so if this is continuous, then all of these are continuous, and vice versa. All right, let's prove this theorem. To prove this, we need to prove both ways. Okay, so this is if and only if statement. So we first prove only if part and then prove if part. Okay, let's prove this direction, only if part. So suppose capital F is continuous. Then by definition of continuity, for any positive epsilon, there exists a positive delta, such that for any x within S, if x is in the delta neighbor of A, then if f of x is in the epsilon neighbor of f of A. Okay, so this proposition holds. Okay, now if x belongs to the delta neighbor of A, we have the following: fi of x, where I is either 1, 2, or m. Okay, fi, so this is less than or equal to the square root of j from 1 to m fj of x minus fj of a squared. Okay, this is because, so one of these j's is equal to I. Okay, so for example, when I is 1, so this is f1 of x minus f1 of a. And so when j is equal to 1, this is the same thing. So, but adding non-negative numbers to this only increases the magnitude of this quantity. Therefore, this inequality always holds. But now, because of this, okay, the distance between f of x and f of a is less than epsilon. But that distance is just this. Okay, this is the distance between f of x and f of a. But because of this, it's less than epsilon, because f of x is in the epsilon neighbor of f of a. Therefore, fi is continuous at x equal to a, right? Because that's the definition of continuity of functions, right? So this epsilon can be any positive number. So for any positive number, we have a delta neighbor that satisfies if this, then this. Therefore, this is continuous. So the only if part is done. Now prove if part. So suppose f1, let's say f1, f2, and so on, fm are continuous at x equal to a. Then, by the definition of continuity, for any epsilon there exists delta. Let's say delta I for each of these. I is 1, 2, and so on. Delta I positive delta I such that for all x in S, we have if x is in the delta I neighbor of A, then we have the difference between fi x and fi of A is less than epsilon. Okay, so this is the definition of the continuous function. Okay. Now, from this, wait a minute. Maybe I should write square root of m. So since epsilon is any positive real number, so epsilon divided by square root of m is also any, it can be any positive real number. Okay, so let's see. Because of this, we want to show that this capital F is a continuous function. So for that, we need to show that we need to find some delta. Okay, so we want to show that for some delta, if x is in the delta neighbor of A, then the distance between f of x and f of A is less than epsilon. So what is this delta? Okay, so let's say delta is the minimum of delta 1, delta 2, and so on up to delta m. So for each I from 1 to up to m, we have delta I. Okay, so let's pick the minimum of these deltas and set that to delta. So that means if x is in this delta neighbor of A, that means the distance between x and A is less than or equal to any of these delta i's, delta 1, delta 2, delta m. So that means for any x satisfying within this delta neighbor, this is satisfied. Okay, so now the distance between f of x and f of A is, by definition, it's this. Fj of x minus fj of A squared. But by assumption, we have this. So this is less than j from 1 to m less than epsilon squared over m. But this is a constant. So this is just so m times epsilon squared m, that is epsilon. So the distance between f of x and f of A is less than epsilon. Therefore, f is continuous at x equal to A. And we are done. Next, let's consider composing maps. Okay, so let's consider three spaces. That is n-dimensional space, and m-dimensional space, and l-dimensional space. And let's consider a subset S. And let's say we have a map. So this is the image of a map. Here's another subset T, and we may have a map from T to the L-dimensional space. Let's call this map G. Okay, if the image of F is contained in T, then we can compose F and G. Okay, so if the image of F is a subset of T, okay, then let's write F is a map from S to the m-dimensional space, and G is a map from T to the L-dimensional space, and the image of F is contained in T, in the domain of G. Then we can compose these maps. So that is G after F. That is S to the L-dimensional space. So that is, we start from here and map it to this, and from here we have a map here. So this whole map is called G after F. This is a composition of F and G. Let's break this down into pieces. Okay, so let's say first we have X, which is in the n-dimensional space. In fact, it is an element of S, which is a subset of n-dimensional space. So if we map this element by capital F, the result is something like this: F1 of X, F2 of X, and so on, and Fm of X, which belongs to the m-dimensional space. Okay, so let's say y, define y as f of x. Okay, then map this point by g. So it will be something like this: g1 of y, g2 of y, and so on, and gl of y, which is a point in the L-dimensional space. So by composing G and F, we have G after F of X is this. So G1, so Y is this. Okay, but F of X is this. So what we have here is G1 of F1 of X, F2 of X, and so on, Fm of X. Then G2 of F1 of X, F2 of X, and so on, Fm of X. And so on, and GL of F1 of X, F2 of X, and so on, and Fm of X. And closing bracket. That's how we define map composition. Okay, here's an example. This may look a little bit intimidating, so let's see a simple example. Let's say f is a map of two variables, f1 of x1, x2, and f2 of x1 and x2. Okay, so this is a map from two-dimensional space to two-dimensional space. And similarly, we define g of x as g1 of x1, x2, and g2 of x1, x2. And the domain and the codomain, they are the same. So let's compose them. So g after f of x is g after f of x1 and x2. And by this definition of composition, this becomes g1 of f1 of x1, x2, and f2, x1, x2, and g2, f1, x1, x2, and f2, x1, x2. This bracket and another bracket here. Okay. So this is how we compose two maps. Regarding composition of maps, we have the following nice properties. That is, if two maps are continuous, then their composition is also continuous. Okay, so let's say here's a theorem. We have f from s to r to the power of m and g from t to the power of l. And assume also that the image of f is a subset of t. So this is exactly the kind of situation we have shown before. So this is S and this is T. So the image is contained in T, and we have some codomain here. So the composed map F and G here. And if F and G are continuous, then okay, if F, G are continuous, then G after F is also continuous. Okay, that's the theorem. Okay, let's try to prove this. Actually, we need to just prove one special case. That is, suppose f from s to rm is continuous map, and g from t to r, so this is one dimensional, okay, is also continuous. So this is a continuous function, and capital F is a continuous map, and lowercase g is a continuous function. So assume this, then it is sufficient if we show that g of f, so the composition g after f is continuous. So this, if we can show this, then that is sufficient. Let's say is a continuous function, let's say. Because from the previous theorem, if we show this, then if for general map from T to R to the L dimensional space, then we can just say each component of this uppercase G is continuous, is a continuous function. Then we can show that this G is also continuous, right? So therefore, uppercase G after uppercase F is also continuous. Okay, so all we need to show is just this. If we can show this, it is trivial to show that this is also continuous map. Okay. All right, so we prove that G of f of x, that is f1 of x, f2 of x, and so on, f of, okay, we show that this function is continuous. That this is continuous. Okay, so first of all, since G is continuous, before that, let's see, let's say A is A1, A2, and so on, AN, and B is f of A. Okay, let us define these 2 points. Okay, it's continuous. By the definition of continuity of a function, for any positive epsilon, there exists a delta, let's say delta prime for the moment, such that for all, maybe we should use y here. For any y in the domain of G, if y is in the delta prime neighbor of B, then we have the difference between G of y and G of B is less than epsilon. Okay, this B is this B. Okay, and also since f is continuous, by the definition of continuity of a map, let's say we have, suppose delta prime is given. So there exists a delta that is positive, such that for any x in the domain S, if x is in the delta neighbor of A, then what? F of x is in the delta prime neighbor of f of A. Okay, this delta prime is this delta prime, okay, that we used here. Okay, so by combining these two, we can say that for any, so in summary, for any epsilon, there exists a delta such that for all x in the domain S, if x is in the delta neighbor of A, then so this holds, right? F of x is in this. But if we say y is equal to f of x and b is defined to be f of A, so therefore that means y is in the delta prime neighbor of B. Therefore, from here, we have g of y minus g of B is less than epsilon. But by the definition of y and b, we have g of f of x minus g of f of A. So difference between this and absolute value of it is less than epsilon. Therefore, g after f is a continuous function. And we are done.